Yeah, so this is Nick Ugusini. I'm an electrical engineer working at NASA Glenn Research Center in Cleveland, Ohio. And we're working on a lunar night survival technique that we call lunar power hibernation. This strategy is to allow solar and battery powered lunar spacecraft to operate past a lunar night rather than just during the first day it lands. But to pull it off, it requires reliable electronics and batteries capable of thermal cycling down to cryogenic temperatures. I've been working with Rich Eftering, Tom Miller, and Brian Haller on this research at Glenn. Rich and I have been focusing mainly on the electronic side recently, and Tom and Brian are more working on the battery side. This presentation will go into some of our findings so far and how we envision the strategy can provide a reliable but low-cost solution for powering lunar systems. So, as we've talked about, and as you probably already know, the lunar surface is a pretty hostile environment. You can see this chart here is temperature data taken from the Lunar Reconnaissance Orbiter. It's the environmental temperature, not including permanently shadowed regions. You can see the temperatures get as high as about 400 Kelvin during the day at the equator and as low as 50 Kelvin during the night. And again, this is not including permanently shadowed regions, which can get even colder, down below 20 Kelvin even. The maximum temperature rate of change is about 5 Kelvin per hour. So not very much. It's even slower in some areas of the moon. The temperature variation depends on the latitude, but it's important to note that no matter where you are on the lunar surface, temperatures will drop below 100 Kelvin at some point during the lunar cycle. And the coldest temperatures occur at the poles, especially during the polar winter, which you can see there at the bottom. Obviously, that's a challenge for spacecraft, especially those that run on lithium-ion batteries. And the lithium-ion battery freeze point is about 200 Kelvin, and you can't operate them when they're frozen. It's also going to be a challenge for the Artemis missions, which are focusing on the south lunar pole, where the environmental temperatures may not even get up to 200 Kelvin in the first place. So without some kind of radioisotope power source or tethering to some kind of pre-in-place power grid, lunar missions can't easily operate past a single day on just array power and batteries. And so we kind of want to set up to change that. So here are some options we can utilize to survive the night currently. The next commercial missions to the moon as part of the Commercial Lunar Payload Services, or CLPS program, are all solar powered. And due to the difficulty of surviving the night environment, they don't currently require lunar night survival for the missions, but they are looking for options to do so. There was a CLPS conference back in December, actually, at Glenn, that talked about lunar night survivability, which we presented at. But the existing options are tricky. They require generating and or retaining heat throughout the entire night to keep all the systems happy until the sun comes back for power and heat generation to resume. But this requires either massive batteries, heavy insulation, consumable chemicals, or a combination of these components to pull off survival. The option that we are exploring is to just disconnect all power at lunar dusk to isolate the batteries from the main bus so they're not being used during the night, and allow all the systems to drop down to the lunar night environmental temperatures, keeping everything frozen, including the batteries, until the sun returns and lunar dawn begins, when we can start generating power with the solar arrays, and then we can enter a controlled thawing process to bring everything back to operational conditions. In order to do this, though, we need the entire payload or spacecraft to be tolerant of cryogenic temperatures and temperature cycling, and we'll need portions of it to be operable at cryogenic temperatures as well. For reference, when we're going through this presentation and I say the word cryogenic, I'm strictly talking about the coldest temperatures during the lunar night, around 50 Kelvin, not temperatures in the millikelvin range, which is another cryogenic region of operation. We're not going to be worried about superconductivity effects or anything like that. We're just going down to 50 Kelvin. So here's a high-level diagram of how we could accomplish the revival process at lunar dawn. The yellow boxes here are cryo-operable systems, or operable while at cryogenic temperatures. And the blue boxes represent cryo-tolerant systems, or just capable of surviving thermal cycling down to 50 Kelvin and then back up to operational temperatures. So the sequence here begins at lunar dawn when the solar arrays begin to generate power again. At this point, all the systems are assumed to be frozen after 2 weeks at cryogenic temperatures, as the sun hasn't been able to heat them. So Because of this, we require cryo-operable power architecture represented as the main bus controller there in the middle to manage the power generated by the arrays at lunar dawn. It would be responsible for regulating and distributing power to the heaters and the battery management system, or the BMS. And the heaters would then begin to heat the cryo-tolerant systems, like the battery and the avionics, so that they can be restored to operational conditions once they've equalized their temperatures. And once that happens and the batteries are fully thawed and the health of the cells are checked out by the BMS before they're fully used, the isolation relay that keeps the battery disconnected during the night would be commanded closed, and then normal operation can resume on solar array and battery power. It's important to note that the time frame for this is such that the environment might still be at cryogenic conditions even after everything has warmed up. So you need to continually, power the heaters, and this would be crucial for missions that are at the poles where temperatures never pass above about 200 Kelvin, which again is the freezing point, approximately the freezing point for lithium-ion batteries. So obviously, cryogenically tolerant batteries are required for this scheme to be successful because you cannot charge or discharge fully frozen lithium-ion batteries, and attempting to do so during the freezing transition period can damage the cells as well, cause thermal runaway, and some other problems. So at Glenn, we've been researching 18650 lithium-ion cells for a few years, and we've shown that these cells can passively survive freeze-thaw cycles without any apparent degradation in their operation, provided you only attempt to charge or discharge them when they're at operational temperatures and not during the transitional state. The cell voltage will drop to 0 volts after they fully freeze, but their charge capacity still recovers to the state it was before being frozen when they come back from cryogenic temperatures. This indicates that freezing and thawing batteries can be a reliable option for powering spacecraft after experiencing the low temperatures of the lunar night. But so far, our tests have only been a small set of cells. We have some more important questions to answer going forward. Questions like, are we missing some part of the bigger picture with just these simple tests? What are some degradation mechanisms we could encounter? How many cycles are tolerable, and what rate of change can we survive? What's the best state of charge to freeze at to maximize the life of the battery? Things like that need to be investigated going forward, and that's what we've started to do to prove the reliability of these batteries for passive storage during the night and then reuse during the day. So our main focus at Glenn is to take these batteries through multiple simulated lunar cycles. We've been focusing on the 18650 format because it is widely popular within NASA and have been used on many missions already. And most recently, we finished testing some 18650 cells at 0%, 20%, and 40% states of charge through multiple thermal cycles in a cryo-cooled chamber. We're focusing more on the lower states of charge just for safety considerations instead of testing fully charged batteries. It's safer to use the lower states of charge. And the results were promising. Both the LG and the Molicel 18650s that we tested survived 2 simulated lunar nights, and it showed no apparent degradation when they came back up to temperature. We acquired other 18650 cells from the NASA Strategic Reserve to test, and we plan to try different pack configurations going forward, including larger series and parallel combinations. And we want to investigate other cylindrical cell formats as well eventually, such as like 21700 cells going forward. So along with our research in-house, we have a few external partners that we're working with to further this battery research. Dr. Hatzel and Dr. Zoe and their teams have been characterizing the freeze-thaw process in lithium-ion cells, both mechanically and electrochemically. They're characterizing degradation mechanisms that the cells may experience, and they plan to get some imaging of the electrolyte freezing in real time. Because we're not exactly sure what actually occurs once the cells freeze that causes the open circuit voltage to drop to 0 volts. So this research should give us better insight into the mechanisms of the freezing process and how to manage that. So overall, lots of progress recently with regards to cryogenic battery research. Now to switch gears to the electronics side that we've been looking at. This is, again, mainly what I've been focusing on recently. To relate this back to the earlier dawn revival diagram on the previous slide, the lithium-ion batteries, again, must be cryo-tolerant. And again, that is capable of operation after experiencing a temperature cycle down to cryogenic temperatures. And all the electronics must also be cryo-tolerant, including mechanical considerations like circuit board assemblies and solder joints. They need to show integrity across the entire thermal cycle. So the entire payload and the entire spacecraft needs to be cryo tolerant. And all this can be influenced by different material types and electronics package sizing, but testing shows that cryo tolerance is attainable for circuit board assemblies. But most importantly, some of the electronics must also be cryo operable for successful lunar night survivability, as you cannot start the heaters without these cryo operable systems, because you won't have the heaters to heat them up to start them up. So cryo operability requires stable operation when turning on at temperatures as low as 50 Kelvin, which we refer to as a cold start, as this is representative of the environmental conditions at lunar dawn, since you will have had a full, more than 14 days of lunar night temperatures. The entire system is going to be at that low temperature. So it has to be able to start up at that temperature. And they must be capable of operating solely on solar array output as well, without any supplemental battery power to back up the main bus. It needs to be able to manage and regulate the solar generated power. And crucially, it must be able to control the heaters to thaw out the cryo tolerant, but not cryo operable systems. And this will require accurate measurements for effective closed loop feedback control while at those temperatures. To this end, we've been developing some cryo-operable electronic demonstrations at Glenn. The picture on the right there of our built test setup shows a sequential switching shunt regulator, or S3R, circuit board that I designed for testing in our cryo chamber. The module accepts inputs from up to 8 solar string simulators to produce a regulated 28 volts DC output. And it was designed with component types that have been shown to be reliable at cryogenic temperatures based on previous analytical assessments of published research that we did in past years. This includes, for example, ceramic capacitors as opposed to liquid electrolytic capacitors, which freeze similar to batteries, thick film resistors over carbon resistors for better temperature tolerance, and CMOS type semiconductors over bipolar junction type semiconductors. There's a lot more other types of parts that are better suited for cryogenic operation, but those are kind of the main ones. After testing and verifying the operation of the S3R circuit board at room temperature, we put it in our cryo chamber and ramped it down to 45 Kelvin, or about negative 230 degrees Celsius. The regulator was operational for the full temperature ramp down over the course of about 2 hours. The set point drifted a bit, but that was to be expected with the temperature variation. Everything stayed pretty stable though. And after operating for a few hours, the regulator was shut off and allowed to fully cold soak overnight, and then was turned on the next day, successfully performing a cold start at about 40 Kelvin and continuing to operate reliably for another 28 hours. We only just begun testing, but this was just last week and the week before, but we have more tests planned for the rest of the year to better characterize and analyze the effects of cryogenic temperatures and the thermal cycling on the electrical operation, as well as studying the mechanical integrity of the assembly itself. So past improving the circuit design and fully characterizing the behavioral changes across temperature ranges, the next steps in our research will likely include integrating software with microcontrollers or FPGAs. We did a really quick test about a month ago with some AT-tiny microcontrollers, just really simple, 8-pin micros, just to see how they would operate. And we just had to send out a heartbeat signal. It was only like a kilohertz just to see what would happen, and it still effectively worked down to 40 Kelvin. It was still pulsing at the same frequency, so it's pretty promising. Eventually, we're going to combine the system with the software with the lithium-ion battery research that the other group's been doing, and design a more complete demonstrator as one unit in a cryo chamber, and then we can begin to simulate actual implementation in a lunar environment in the lab. So like the battery research, we are also working with external partners on the electronics research as well. Dr. Zhang is focusing on gallium nitride HEMTs, which are shown to be they actually show an improved operation in many aspects at lunar night temperatures as it gets down to the really cold temperatures. Dr. Zhang's team is characterizing the devices across the full lunar temperature range, not just cryogenics. They're identifying the potential degradation mechanisms and how to mitigate those degradations, and they're developing their own GaN-based power systems for potential implementation of the hibernation strategy. So we hope to leverage his research in future designs going forward. Another program that's putting out a lot of research relevant to our interests is Luster. and that's made up of researchers from the University of Tennessee, Auburn University, and Georgia Tech. Their work is independent from the lunar hibernation research, but their focus on cold-tolerant electronics and packaging for lunar surface exploration is obviously relevant to our research. And some of the work included here includes developing custom devices in silicon and silicon germanium. Radiation tolerance is another area that topic 3 covers that we should be focused on if we want to eventually use these cryo circuits on the moon as a flight demonstrator. So we also, plan to infuse this work going forward whenever we're able to. So eventually we want to develop design and operational guidelines for cryogenic use of electronics for spacecraft applications based on our research, both previously and our current research. This would detail component types that are suited for cryogenic use, packaging strategies for the parts and the assemblies, suitable material types from the circuit boards themselves to the type of solder used, a lot of things like that. There's many aspects to producing reliable, cryogenically tolerable and operable electronics. So there's a lot of work to be done in fully fleshing out this research. And groups like the NESC and programs like NEPP will likely be crucial in maintaining guidelines and standards for cryoelectronics. The culmination of this research can be used for designing a ground-based technology demonstration for use on a CLPS mission. And ultimately, we would want to make a flight technology demonstrator to fully prove the hibernation strategy. And this could take the form of a separate CLPS payload, or it could be integrated into the CLPS lander itself. And it shouldn't have much impact to the mass or cost of the mission. And this tech fits right into the Artemis program as well, because it can be used on robotic lunar rovers, or even as part of the lunar base infrastructure itself that the later Artemis missions are planned to deliver to the lunar surface to build up. To summarize, utilizing the discussed cryo-operable and cryo-tolerant electronics in order to revive lithium-ion cells from a frozen state will enable reliable operation of low-cost robotic missions across multiple lunar cycles. Integrating hibernation in this way will have minimal impact to the design of existing spacecraft and payloads, as it does not change the battery capacity or the mass, and the changes are limited to only the main bus controls and the battery management systems if they are not currently cryogenically operable, and it'll have minimum impact on the development costs if implemented early in the process. So we're living in an exciting time where lunar exploration is coming back into focus. And through this hibernation strategy, I think that we can achieve reliable, low cost, and long-lasting lunar exploration missions. That's all I got for you. So here's our contact info, and we'll be taking any questions.
Thank you so much, Nick.
Yep.
I think it's really exciting, the potential for this to allow CLPS landers to last more than one day. Mm-hmm. Yeah, definitely excited about the infusion path as well. I did see one question in the chat that Richard answered, but I think I'll go ahead and ask you as well. So why use solar panels here for heating instead of using a direct solar heater?
Sorry, what was the last part?
So meaning, why have solar panels power a heater rather than using the sunlight directly?
Oh, okay. So that is another option we could do. The downsides to that are that using the sun to heat everything up would likely take longer because you'd have to wait around for the whole system to passively heat up. And this might not work at the poles. I think I mentioned that the environmental temperatures around the poles don't pass the thawing point, the 200 Kelvin point where the lithium-ion cells freeze. So that's another barrier. We would need active heaters in that case as well. So certainly along the equator, that could be a viable option. But if you're looking more at the polar implementation, you're probably going to need some kind of active heating.
Got it. That makes sense. Let me see. I don't see any others in the chat, so I'll go ahead and
actually, I did have a question for you. I guess I'm on the wrong sequence in terms of the viewers. But the question comes in is have you considered the use of eutectic materials at all?
So the strategy we've been looking at is, mostly electronics. So we don't have much experience in materials. So that's something that we could explore. I'm not really familiar with any of those.
I strongly recommend, it was actually used for the Apollo lunar rovers.
Okay.
Actually it was beeswax, I believe. But there are multiple eutectic and so-called dual or tri-eutectic materials where, depending upon the temperature range, they either are exothermic, endothermic, or essentially just act as a heat pipe.
Okay.
And so there's some very interesting, potential there.
Great. Okay. Yeah, we'll definitely look into that. Thank you.
Thank you for that insight, Gary. I have one quick question before we move on over to a Jen. So the theme of this workshop is really reliability. So I'm wondering what you envision as the weak link in this whole wake up process.
I think the big question mark right now is probably the battery cells, just because we need to do more research into different formats and need to do more rigorous testing of the cells. We've only done a few cycles, and I don't know. I know we found research on the thermal cycling of the cells as well, but that's a very volatile point, the batteries themselves. So I think that's probably the linchpin. But the good news is a lunar night or a lunar cycle is a month long. So you only have to survive a temperature cycle once every 2 weeks or so, right? So even if it's only reliable across 5 or 10 cycles, that's still, you can still get a year out of a mission, whereas before you'd only get 2 weeks, right?
Yeah,
so
that's definitely a big jump.
Yeah, I think the batteries is the part we have to look at most.
Okay, great. Yeah, that was a topic that came up a lot in our energy storage breakout room last night. So definitely interested in hearing the results of more thermal cycling.
Yeah.
Okay. Well, thank you very much, Nick.
Hey, thanks a lot.
Thank you. All right, so we'll move on to our next speaker. So next we have Jen Wong of the Ohio State University. Jen, are you there?
Yes, can you hear me now?
Yes, I can.
Okay, great.
If you want to go ahead and share your screen.
So I just enabled my video, but during my presentation, I would turn off my radio for the sake of the stability of the internet.
Sounds good.
Okay. Well, so I guess I can start.
Please do.
Well, I'm Professor Jin Wang from The Ohio State University. We are at the Center for High Performance Power Electronics. And in our center, our works are mainly focusing on high power, high voltage power electronics.
Jen, we can no longer see your screen, sorry.
Okay, sorry. Okay, I think I disabled the wrong thing.
No worries.
Thanks for letting me know. Well, again, as I just mentioned, we are mainly focusing on high voltage, high power applications, and these days, about 60 to 70% of our work are more about aerospace applications. So in today's talk, I will cover 2 projects we are working on. One is a Lustre project on microgrid. The other is a competition, the Watch on Moon competition we are participating in this year and moving forward to the next year. So the Lustre project is a collaboration between Raytheon Technology and us. The purpose is to study the power regulation reliability, sustainability of interconnected lunar microgrids. The purpose is saying, okay, we need to make sure that each small microgrid, for example, the habitat, would be self-sufficient. But at the time, if we have actual power from one microgrid, and we can actually optimize the power usage. And also at critical conditions, we can utilize resources from other microgrids to support critical load in another microgrid when the power source was lost in the microgrid that was in trouble. So you can see we have 4 microgrids that we have started, and they are interconnected together with a ring network. At the connection point of each microgrid, we have this DC energy router. So this DC energy router has multiple functions. The main function is to basically realize the power flow control, and also it can have circuit breaking, fault current breaking capability, and power quality improvement capability. So in terms of each microgrid, we intentionally selected a different architecture for each microgrid. We are still not certain exactly what kind of topologies we would have in the habitat, in the charging station, or SRU, or the lunar science experimental stations. So what we try to do is to implement as many types of architecture as possible. So later on, if in a real lunar microgrid, we would implement one of these or multiple of these type of microgrids, we can have solutions readily available. And in these microgrids, we have critical loads, we also have non-critical loads. We have their own energy generation units, we have energy storage units, we also have energy routers inside each microgrid to make sure that the power flow between sources and loads are maintained in an optimized fashion. One thing I would like to point out is that indeed, for each microgrid, the energy router would help us to not only to satisfy the load and source balance, but also help us to mitigate the failing mode conditions and improve the power quality. So the approach we have taken is to look at both the design and operation, because now we are looking at the space system, so we own both the source and load, which is quite different from the electric power distribution networks on the Earth. So in this way, we can start with optimization of the source, load, and energy storage together. And then once we have the optimized design, we can optimize operation. So in terms of technical approaches, we have 3 layers of research activities that go along with each other. At top layer, we are using graph theory to do the reconnection strategies, to do the fault analysis, and basically to help the second layer, which is the energy management system, to do the real-time reconfiguration and the power flow optimization. And the energy management system mainly was designed and implemented by recent technology. It can help us to do the planning in terms of hours and also in terms of minutes. So basically we have 2 time scales. And then at real-time operation, we often would run into dynamic situations. So you can see voltage fluctuations, load fluctuations. That's really that at the bottom layer, we are using what we call smart resistor control to try to optimize the power flow, to improve the stability during voltage and power transients. The smart resistor control was a concept we proposed doing another NASA project, which was for aerospace, which was for the propulsion for electrical aircraft. In that application, we have to coordinate multiple energy sources together with a lot of constant power load. So the purpose of smart resistor control is to make all kinds of loads to behave like a passive resistor. Then fundamentally, we can get rid of stability issues, no matter it's at voltage transient or load transient. And that is based on high bandwidth power electronics and also distributed energy storage. And this is the energy router. The architecture of the energy router is from our earlier APA-E project. During the APA-E project, we worked on 2 prototypes of a T-type DC circuit breaker. So you can see the energy router has a T shape. It has 2 horizontal arms and 1 vertical arm. In the APA-E project, we were using silicon carbide devices because those are mainly for aviation and also for shipboard applications. The voltage rating were at 1 kV and 20 kV. But recently, we demonstrated 20 kV 50 amps circuit breaker with the 3.3 kV silicon carbide power module based some modules. And with recent technology, we demonstrated 1 kV 500 amp circuit breaker. In this project, we are using 200 watt gallium nitride based hand for the 120 watt DC distribution we have. So again, we have the circuit breaker capability, and we realize and regulate the power flow. We improve the transient stability and also improve the power quantity with the energy router. So why we say this is an energy router? The main reason is that with this modular structure, each sub-module of the horizontal arm and vertical arm can be seen as an independently controlled voltage source. So then what we can do is a series and a parallel compensation, like what we are doing in AC systems nowadays, especially flexible AC transmission systems. You have fixed devices to do the series and the parallel compensation to make sure the power network to be stable. Here for the DC system, we are doing the same thing. So we are inserting all these equivalent voltage sources to help us to regulate the power flow control, to optimize the power flow, and also in terms of transient conditions, improve the stability. So again, with this structure, you have the ultimate ways to help with the stability improvement and also steady state compensation. And this is status of the development. We successfully tested our 200 watt gallium nitride based energy router recently for both continuous operation in terms of power flow control. On the right hand side, you can see the picture of the prototype, and also on the lower corner at the switching test of the prototype. We have very clean switching waveforms during the double pulse test, continuous double pulse test, as you can see from the waveforms. And on the left-hand side, that's the breaking test result, which was achieved just a couple of weeks ago. We, as shown in the circuit architecture, to achieve the capability to transfer 10 kilowatt of power at 120 watt, and also to break high current, we have 2 branches in parallel. So then in the waveform, what you see is that we have 2 current waveforms. One is green, the other is purple. Those actually are the 2 branches of fault current when we are trying to shut down the fault current. And the blue curve at the top is the voltage of the sub-module capacitor. In this case, we haven't connected our energy router with a battery, so we only have local small capacitors. And these capacitors are absorbing all the energy actually stored in the parasitic inductance of interconnection cables of the system. That's the reason during the breaking event, you can see this capacitor voltage goes up, but that's within the design range we have. And the current waveform, the green and the purple one, show that indeed we can break 240 amp without any issue, and within 60 microseconds, the current can be fully cut off. So the next step actually would be demonstration. So we are building a hardware testbed with 2 emulated sources and 2 emulated loads. And to make things more challenging for us, we make both loads as constant power loads. We understand in the real system, you would have a lot of legacy loads which are resistive, but here, just to make things more interesting and challenging for demonstration, we make the loads as constant power load. And the testbed hardware had been fully tested recently. We are doing the programming, trying to see how we can start to do the demonstration step by step. Then besides the hardware testbed, we do have all-party based real-time simulation. And in the real-time simulation, which was already completed early this summer, we have the 3 microgrids and also a zone of the habitat. So in the real-time simulation, we are simulating almost the whole interconnected microgrid, and we have a power amplifier, which is silicon carbide based, to connect the real-time simulation with the real hardware testbed. In the final demonstration, which is planned for November this year, we will show the normal operation and we will show 2 fault conditions. So this is in progress. Please stay tuned for our next presentation I hope actually we will present in October in LSIC workshop to show our updated results, especially from the testbed. So the next topic, very quickly, I will talk about our progress for the What's on Moon challenge. Some of you may be very familiar with this challenge. So it is to transmit 1.5 kilowatt of power over 3 kilometers of distance on the moon surface in simulated environment. The source voltage is 120 watt. The load has a voltage ranging from 24 to 32 watt. The ambient environment is 77 K, it's the liquid nitrogen temperature, and it is vacuum condition. And our approach is to transmit the power with high voltage DC. So we basically are using 1.5 kV DC distribution. In this case, we are using isolated DC-DC converter to boost the voltage to 1.5 kV and then step it down to 24 to 32 watt. Energy storage would be stored on the low side. We initially have chosen lithium phosphide battery because it's very safe for my students to play with. But the problem of this battery is that maybe it's not ready for vacuum operation. For cryogenic, we can use external heater and also internal power loss of the battery to maintain the temperature, and also multi-layers of insulation. So in terms of implementation, the first thing we looked at is radiation hardness. These are two groups of papers published by NASA in the last couple of years. You can see for silicon carbide devices, single event burnout still can happen very quickly, especially for 3.3 kV device. The single event burnout happens around 700 watt. So that means it's not very ready for space applications. For low voltage rated silicon carbide devices, things actually, we also have similar issues, but some of the devices are gradually getting there. For example, one of the devices has a single event burnout happening over 1000 watt. But for gallium nitride devices, if the voltage is lower than 200 watt, if the rated voltage is lower than 200 watt, most of these devices actually can be considered as radiation hardened. When the device voltage reaches 600 watt, these devices would have single event burnout around 350 watt when the DC voltage is 350. So if we use 600 watt rated devices, we have to de-rate the device to make them safe for space application. For cryogenic operation, as several talks had discussed in the earlier part, there had been demonstrations. I think reliability is the issue, but to do short-term demonstration, it's no longer a problem for silicon carbide and gallium nitride. University of Tennessee even demonstrated 100 kilowatt silicon carbide in water in cryogenic temperature. It's the long-term reliability that nobody has demonstrated yet. Then for the circuit topology, as you can see, I'm still using a modular structure. This is a modular multi-level converter structure. We are operating this in a non-traditional way. We basically are doing very low frequency switching. It's 60.67 kilohertz switching and a very small duty ratio, but phase shifted from some module to some module. In this way, we can do frequency multiplication and also voltage step down even before we reach the transformer. So after this modulation, before we reach the transformer, the voltage is already stepped down from 1.5 kV to plus minus 150 watt. And so what you see would be a square waveform, and also on top of that, because of this modulation strategy, the frequency the transformer sees is 200 kilohertz. So we have 3 times of frequency multiplication. And the size of the magnetic core could be smaller because the frequency is no longer 6.7 kilohertz, it's 200 kilohertz. So we have a couple good features of the circuit topology. Another thing is that for each SAR module, the DC voltage for each SAR module is only 300 watt. That means if I use 600 watt rated gallium nitride device, it still could be considered as radiation hardened. And this is the test results or evaluation results we have for the gallium nitride device, the Infineon gate injection transistor, which is 600 watt rated. And you can see indeed at a lower temperature, at a cryogenic temperature, the on resistance is greatly reduced when it is compared to normal room temperature. And on the right-hand side, you can see the switching waveform at cryogenic temperature. We can design a circuit, operate for hours at cryogenic temperature without any issue. And then we also need to look at the main magnetic component, the transformer. So we have chosen the nanocrystalline core for this purpose. And what we see is that at the lower temperature, somehow our core loss would increase. That helps a little bit in terms of make the transformer core to operate at its optimized temperature point, but also it can generate thermal issues because in the vacuum condition, the only way to dissipate heat is radiation, and transformer usually is put in the middle of the circuit. Then how we radiate this heat to make sure we do not overheat the transformer itself or components around it, that's something we have to consider. So again, for this particular core, we see a slight core loss increase at a lower temperature, especially at a lower frequency. But at the switching frequency, 200 kilohertz, the frequency we're concerned about, the change is only 8.3%. So we're done. Yeah.
Just a heads up that you have about 4
I need
minutes left.
1 more minute.
Yep.
Good. So we demonstrated this back in March. So we had operated this in our lab continuously for a single SAR module for hours. So we were very confident. So during the judging event, we operated 1 SAR module in cryogenic and vacuum condition. You can see the waveform. It's a typical switching waveform you would see from half bridge, and it worked out pretty well. For the system level demonstration as a university team, we feel that it's not only a technology that we are developing for university team, we also need to use this opportunity to really inspire our students. So we basically made this not only a technical demonstration, but also a public event. Another reason for this is we really want to see what would happen if we do use a 22 gauge cable for DC transmission for 3 kilometers. What if we have loads kicked on, kicked off, and what kind of trends we would experience, whether that would cause issues to our control of our isolated DC-DC converter. So our students took 2 days to lay 6 kilometer long of cable on the ground in our test ground, and to form a very large NASA logo, as you can see from this picture. And the demonstration after 2 rounds of trying eventually worked very well. And on the load side, we have a TV, we have a speaker. So once actually the power was successfully delivered, these loads kicked on one by one, and the TV started to show President Kennedy's speech, "We go to the moon." We showed part of it, and followed by OSU fight song. So far actually we're okay with our prototype. We are still doing a lot of studies, especially on thermal management. So actually I need 1 more minute. I forgot I do have 1 extra slide. So the thing we identified is that indeed the weight of the power electronic system is 2% of the overall system. The cable is about 33% in terms of weight, and the battery is 64%. That means actually if we go to higher DC voltage, we may reduce the size of the weight of the cable. And if we go to AC transmission, we potentially will have another benefit of cable weight reduction. And in that case, we'll have to increase the weight of power electronics, because the complexity of the power electronics will go up. But still, it's 2%. If you add another few percentage, it's not significant. So the takeaway is that there's still a lot of studies we need to do, especially interdisciplinary studies, and a forum like this would be very helpful. Thank you. That's all I have.
Thank you very much, Jen. I'll remind everyone, if you have any questions, to please put them in the Q&A. I think we have time for one or two. So just one that I wanted to ask real quick. So yesterday we in the breakouts, we talked a bit about maintenance. So for your energy router, if we needed to, so like if a single event burnout took out one of the arms of your router, how would you envision doing maintenance on it?
Well, it is actually based on the architecture is more or less based on modular multi-level converter. You can see you have a lot of modules connected in series, and we definitely can do N+1, N+2 design. So if one module is out, we can take them out. But that means you also need to have some bypass switches or bypass connections you would enable on the way. Those actually could be mechanical ones. They do not have to operate all the time. So I think indeed this approach, the modular approach, enable you to do that safely. Yeah. And also potentially easily, but still it's a lunar environment. How we're packaging that to make that easily serviceable, that's something we haven't been able to work on.
Thank you. Okay, I think that brings us to time. So I will thank you again, Jen, and thank you also to Nick for both your great talks. And I'll pass it over to Matt.